Hey class, this is Mr. Schmidt. I will do one last video describing the final exam. We'll go through all the questions. One thing to note, different tests had different athletes. So I'll go through the process and then at the very end, I'll show you the spreadsheet that has all the final numbers on it. All right, so this one, Simone Biles is our athlete, but like I said, the equations in the process should be the same for all of them. All right, so the first question, what is the net impulse delivered by this force? Okay, so one thing you need to know is change in momentum is impulse, okay? And if change in momentum is impulse, we can use that as force times change in time, which is going to translate to area. All right, so triangles, of course, are 1/2 base times height. So I'm going to do 1/2 times 4 times 5. Okay, so that's going to give me 10. 1/2, I guess my base is 5, my height is 2. This is going to give me another 5. Here's a rectangle, 5 times 2, 10. Now, here's the biggest issue we had. We have an area up here, okay? This is in the positive, and we have an area down here, which is in the negative, and it's split exactly in 2. So the net result is when we add this and subtract that, we get 0, okay? So we add all those numbers together. Okay, and that is newtons times seconds. All right, so if that is our momentum, that is our net impulse, we can also say momentum equals mass times velocity, okay? Or velocity is momentum over mass. Okay, so here is going to be our momentum. And whatever number you have up here is going to be your mass. Okay, like I said, I'm going to show you on the spreadsheet at the very end what the answers are for the different variations of this test. Okay, now how do we do net work done? Okay, so work equals change in energy. That's one way we can do it. All right, so we don't necessarily know the starting speed, but we know it's change in velocity. So we can do 1/2 mv squared. Okay, and again, both your v and your m are going to be based on your athlete now. Okay, some people did ask, yeah, the assumption is they're starting from rest for that to work. All right, that was number 1. Number 2 is, where is it? What is the final speed and direction of a combined group? So we have 2 things colliding, okay? So we have, while walking north, okay, so this is your athlete. It runs into Naomi Osaka. All right, so we have mass of Naomi over here. All right, she is traveling west. So that's V Naomi. And our velocity of our athlete is 3 meters per second. All right, so what is the combined momentum of this group? So this is where we see a triangle math type piece here. All right, so we need to do our momentum in the X, momentum in the Y equals our momentum total squared. It starts, our only Y is this one and our only X is that one. So we're going to do mass of our athlete times velocity of our athlete, mass of Naomi times velocity of Naomi is going to equal p squared. Okay. Or we could also call that and mass of Naomi times v final, all that squared. Okay. Again, it's going to be contingent on which athlete you have when I show you those final answers. All right, moving on here, what is the change in kinetic energy for the system? All right, so that means you're going to have to do okay, remember what I'm doing is E equals E prime. Okay, so the masses stay the same, but we have our initial velocities. Okay, our initial velocities are still true, but we're going to have our new velocity is going to plug in here. Okay, and here's the whole point. These two are not equal to each other. Why? This is not perfectly elastic. Okay, so first of all, they are not going to equal each other. Okay, what we want is E final minus E initial equals change in energy. Okay, and what we expect to see is that it's going to lose energy due to the collision. Okay, and again, mass dependence, so we're going to look at that on the spreadsheet at the end here. All right, so number 3, draw your force diagram. Okay, so what do we have? We have our force of tension going this way, we have a force of gravity going that way, and we have our force centripetal going this way. Okay, notice this angle from the horizontal is only 5 degrees. Okay, which means this is not really to scale because it's going to look much more like this. Okay, where our force gravity, force centripetal, and our tension. Okay, it's going to be a similar triangle. They're both going to be 5 degrees. Okay, when we also figure out the radius. Okay, so use the force diagram to predict the centripetal acceleration. Okay, so again, we can use the mass of the athlete, which in fact is not going to be fairly significant because force of gravity is mass times gravity. Okay, and our force centripetal is mass times centripetal acceleration. Okay, and we know that if this is our force of gravity and this is our force centripetal, opposite over adjacent is tangent. Okay, what was my opposite? What was my adjacent? Notice how those two cancel out. Okay, so we do get a number for that one. Okay, so that should be true for all of them, that A sub C is going to equal our 0.85. Okay, so that is my centripetal acceleration. Okay, not to be confused with angular acceleration. Remember, centripetal acceleration goes radially, angular acceleration goes around the circle, okay? Presumably this is having a constant speed, so zero angular acceleration. All right, so now we can plug this in, and this is where masses will start to come into play, because we'd have our force x squared plus force y squared equals force tension, which also happens to be force total, squared. Okay, and so here we'd have mass times centripetal acceleration squared, mass times gravity squared equals. Okay, so again, your masses will determine the answer here. All right, and then predict the angular velocity here. Okay, so here we can do either of these. We know centripetal acceleration. Okay, so we can do v squared times r to get our angular velocity. Okay, and if everyone has, remember, mass divided out over here. So this is one where we should all get the same number. All right, moving on from there, we have our object and moving, and one of the things that got people, they looked at this and they thought disk, and they didn't look over here and think point. Okay, we have our metal is moving like a point mass along the outside of this thing. Okay, so make sure you think about not just what the object is, but what way is it moving. Okay, if we had the metal and it was spinning through the axis here, then you'd have to use the disk equation. But it's spinning here, so we have to use the point mass equations. Okay, so that will come up later here. All right, so first, what is the linear velocity of the metal, assuming the length equals 1/2 their total height? So we're going to have to use radius equals diameter over 2. Okay, so you'd have to look up back on page 1, what is their height for your athlete? Okay, you're going to divide that by 2 to get your radius. Okay, and you have 6 revolutions per minute. So if I multiply that by 2 pi to get radians, and if I multiply or divide that by 6, excuse me, yeah, 1 minute is 60 seconds. Okay, then I can get my radians. And again, this is not dependent. This angular velocity should be the same for everybody. Okay, and that is 0.62. All right, remember, it's good to carry out these numbers in the middle of your calculation and then do your rounding at the end. Okay, so that was radians per second. Okay, because now we can do our linear velocity equals r times omega. Okay, so now we have our angular velocity. Your r is going to be dependent on your height of your athlete. Multiply those two numbers together. Okay, what is the angular momentum of this one? Okay, so this is where we're going to have to use the point mass formulas. Okay, so I printed this off. So this is one thing we kind of left the AP questions. I wasn't sure if they were going to throw this in there. So we have all these for disks, But what we really want is the one for linear equations here, okay? It should look just like this. We have a metal, it's spinning, I equals mr squared, okay? All right, so your M in this case is the gold medal. So M equals 0.6 kilograms, but your R is going to be dependent on the height of the athlete. Okay, so that gives you I, that gives you your angular, your moment of inertia, but we want your angular momentum, okay, which means we're going to take this number and multiply it by this number. Okay, once again, that's another reason why it's always good to show your steps, is because you can frequently pull information from previous parts and reuse it and not have to calculate angular velocity multiple times. All right, and then finally, centripetal acceleration of the metal. Okay, that would be an easy way to do it. Okay, again, we're going to use this number, we're going to use that number, okay, get our new value. All right, moving on from there, last page. All right, what is the initial momentum, the initial moment of inertia for the athlete? I don't know why it was so hard for me to read that. What was the initial moment of inertia for the athlete? All right, so we have to keep track of which one is the coach and which one is the athlete. So we say they run and jump into the arms of their coach for a brief moment. The athlete behaves like the rod. So this is going to be, okay, and the stationary coach, who's a thin spherical shell. So this is going to be, okay, I don't know any coaches who are spherical shells, but we just threw that in there. All right. So what's the moment of inertia for the athlete? So they are a rod, and I try to very clearly show which type of shape to use. So you should see it look just like this. So we have 1/3 L squared. Okay. So again, that length is going to be the length of the athlete. Okay. And the mass of the athlete. Okay, so you're going to get your value based on your athlete there. And that gives us, right, so that's, we're just asking for the moment of inertia, yes. Okay, and then what is the common final velocity of the system? Okay, so here we're going to have to use L equals L prime. Okay, so this was giving us I. Okay, so now we can use, just lost my thought here for a second. Yeah, we've already done this one. L equals I omega. So we can do I1 or I athlete plus. Okay, so the coach somewhere stationary. Okay, so that means this one is 0. Okay, your athlete has a starting velocity, and you just figured out that number. Okay, so you take this number down here, multiply it by your radians, okay? and that'll give you over here. Now we use the same one here, and you also need to figure out your I for your coach, okay? It is a spherical shell, okay? So that number is going to go in here, which, by the way, everyone had the same coach, so that was 32 kilograms meters squared, okay? And then of course, we're trying to solve for these because these two are equal to each other, okay? So you should have something that looks something like equals. Okay. All right, because they run and jump to each other's arms, so they're going to stick together. Okay, one's a rod, one's a spherical shell. Okay, and like I said, they're sticking together, which is what we're seeing here. All right. Last but not least, number 6. What is the average angular acceleration? Okay, and what are we trying to look at? All right. Then they tried to get a hoop-shaped metal. Okay, so we have a hoop here. Not the best image I could find, but the point is it's supposed to be hollow and spinning, okay, across this axis. All right, which is going to be important when we look at our options here. Rather than doing this one, about the symmetry axis, we're going to have it spinning about the diameter. Okay, so we're gonna have to do I equals 1/2 mr squared. Okay, all right, so, but first we want our angular acceleration. So in a previous question, we had centripetal acceleration, angular acceleration. We're now going to do our change in angular velocity over change in time. Okay, and it goes from rest to 30, all within 0.5 seconds. Okay. Okay. Notice we don't have any information about the athlete, so everyone should be getting the same answer for this. All right, next one. There's different ways to solve this. The angular displacement during this time. So we can do okay. We can set the initial point to 0. It started from rest 0, so we're going to do 1/2 60 radians per second. By the way, that was supposed to be squared times 0.5 seconds squared. So that should have given you 7.5 radians. Okay, that's all happening within 1/2 second. So it's fairly quick. All right, and then next up, what is the torque required to accelerate it? All right, so torque equals I alpha. Okay, so now we're seeing why we needed I here. Okay, and we already have alpha. So this torque, by the way, 1/2 times 0.6. Okay, make sure you're using R, not diameter. Okay, and you're in meters, not in centimeters. Okay, and then that should give you, we're looking at number 6 here. Very small number, 0.000365. All right, and that should be newtons times meters. Oh, 3675. Okay, And how much work did it take to spin it? Okay, here you can do your kinetic energy again, or you could do times. Okay, either one of those should return the same number, which is 0.165. Okay, joules. All right, so hopefully with that, you see what equations we're looking for, especially for grade defense purposes. It's important you have the right equations to show that you've mastered the standard. Your number wise, let's go ahead and drag that over there and show you the answer key. Okay. All right, so our Simone Biles are, can't remember the two other athletes, KW and BG. This is a decathlon athlete, and this is a basketball player. Okay, I just need people of different heights. As far as I know, they're all going to qualify in Olympic trials here very soon. Okay, but what we see, your equations remain the same. You input the different numbers and you get the different variations there. Okay, all righty. So I will see you all later. And those seniors, I hope you have a wonderful summer and good luck on your next year.